Welcome to section 5.6. This is going to give us another opportunity to solve log equations, something that we did certainly in intermediate algebra. Nothing's changed since then. We'll just have to remind you, ideally, of how to solve log equations and go through the process. So the first type of question that you can have, there's really two types. You can have something of two forms, log base b of something is equal to a number. So if you can get a single log equal to a number, then the best way to solve this is to translate into its exponential statement. Most of the questions will be geared this way because that's what you see most often. There are times, though, because of some complexity, we have log of something equals log base b. It's got to be the same base of something else. And whenever that happens, you know that logs, you've seen their graphs, and you know that they're the inverse function of exponential, so they're 1-to-1. So if you have the same y output, if log base b of something is equal to log base b of something else, then the x's or the inside pieces must be equal. And so you simply just set something equal to something else. You set those inside pieces equal. It's bad to say that you're canceling out the logs. You're using the property of them being 1-to-1. I know that it upsets some people when I say, well, you got to be careful with your language. Like, well, this is how I told myself to do it. We're worried about future applications. Like, for example, I saw people in trig drop signs and stuff, and that's not a good thing to do. So what are the problems going to look like? Very nice, right? They're going to be just like you were done in intermediate algebra. So there'll be something like this. Each one of these I saw in the homework. So log base 3 of 5x minus 1 is equal to 4. Should be an easy problem. What do we know? We have a single log is equal to a number. So what do? We just translate it to its exponential. The base is 3. The exponent is 4. And it's equal to 5x minus 1. So what's 3 to the 4th? 81. 5x minus 1. So that's 81 is, going to add 1 over, right? So that's 82 is equal to 5x. And we're going to divide by 5. So we're not so concerned that we get beautiful answers. 82/5 is an appropriate answer coming out of that. All right, second question, right, that I saw in there. Log base 3 of x plus 3 is equal to log base 3 of 10. Again, any of these problems we would see in an intermediate algebra class. Hey, the logs are the same, and it's a single log equals a single log. So perfect, those inside pieces must be equal. And we're done as soon as we move over the 3. Now we should check just to make sure that the 7 doesn't cause us to take log of a negative, and it doesn't. So there's our answer. Okay, and so that's what we're doing. We're just solving these guys. They'll take time to remind us something. How about this one? Log base 5 of the absolute value of 2x minus 1 is equal to log base 5 of 31. So what does that mean? It means the absolute value of 2x minus 1 has to equal 31. Another intermediate algebra is what I should say. Another intermediate algebra solving. Hopefully you remember your absolute value equations. Certainly you know that what's inside the absolute value could flat out be 31, or what's inside that absolute value could be negative 31. And so we would set the two equations equal to one another. So we move over the 1 in each case and get 2x is equal to 30, or 2x is equal to, I would add 1 here. So let me get an eraser here, get rid of that 30. If I add 1 to both sides, that's a 32 there. If I add 1 over here, I get a negative 30. divide by 2, divide by 2, divide by 2, divide by 2. X is equal to 16, x is equal to negative 15. Both are keepers. Neither one will have us take log of a negative or 0, because no matter which one I plug in, I'm going to get a value and then take its absolute value, so the log will handle it just fine, as long as it's not 0. But both of those make us get a 31 or negative 31 in there. Awesome. So a nice quick reminder of that. They'll have things like this. This is the fourth problem I wrote down. 4 log 2 of x is equal to negative log base 2 of 32. So what's important to realize is that these logs, these two statements that we made up here, log base b of something is equal to a number. What's important is that they're single logs and there's nothing out in front, right? If there's something out in front, I got to fix it. And that's why they care so much about the properties of logs. Because with this, the first thing that you should do is say that this is log base 2 of x to the fourth is equal to log base 2 of 32 to the negative 1 power. Get those in this case, factors up as powers. So what do I know? I now know I have a log base 2 of something equals log base 2 of something else. It would not have worked if I left the 4 and the negative 1 as factors. So what do I know? I know x to the fourth is equal to 1 over 32, right? That's what 32 to the negative 1 is from pre-algebra. That was a true statement right there. Pre-algebra was the class that was taught in. So what's that mean? X is equal to the fourth root of 1 over 32. Well, the fourth root of 1 is 1. The fourth root of 32. Let's think about that. 32 is, didn't mean to put a line underneath it. Let me back that out of there. 32 is 2 times 16, which is 2 times 8, which is 2 times 4, which is 2 times 2. Well, that's 5 2's. So this is the fourth root of 2 to the fifth. Awesome. What's the fourth root of 2 to the fifth? Well, I can pull a 2 out, and I'd be left with the fourth root of 2. Okay, interesting. Coming through there. So that's what we have. 1 over 2 to the fourth root of 2. Now, we don't like leaving these guys in there, so I got to take this as the fourth root of 2 cubed. So they're going to take a time to have us rationalize this. So what's x equal to? It's equal to the fourth root of 8, right? That's what 2 cubed is. All over, 2 is going to come out of here to join the other 2, all over 4. That would be the end answer there. The fourth root of 8 all over 4 would be an appropriate answer. So interesting that they chose that, right? They're having us play around with rationalizing the denominator. I'm hoping that they'll make you do that. But I don't see anything that we did incorrectly in there, right? 32 to the negative 1 is 1 over 32. It's a fourth root in there. So it would have been nice if they had the fifth root, but they had a fourth. And so what we had to do, and I'll highlight it, is we had to introduce, let me go here to a highlighter, we had to introduce 3 more 2's to both the top and the bottom. Why? To get 4 2's under there to rationalize it. So they respect your math, right? That you've done a lot of good math in this process of getting to this class. Other ones are not so bad. You can think, oh my goodness, it's going to get bad. It's not going to get bad. Log of x plus log of x, got to read my writing here, minus 9 is equal to 1. Perfect. Now what we don't have is a single log, so don't start doing crazy stuff. Always get things to be a single log. So this is a log of x times x minus 9 is equal to 1. What do you do when you have a single log equals a number? You use the exponentials. So think back to that first section where they introduced logs, either in intermediate algebra or here. You know what that base is. The base raised to the power needs to be x times x minus 9. Or 10 needs to be x squared minus 9x. Where are we? Beginning algebra. We got to get 0 on one side. And hope that it factors, and if it doesn't, we'll use the quadratic formula. But it does. And so we get two answers out of this. We get x equals 10 and x equals -1. But you and I, we're good. We've chosen a math route. So we know we're not going to just take two answers, especially in something that has a limited domain. We're going to make sure anytime we have a limited domain that the answers are legit. So let's check the 10. Can you take the log of 10? Absolutely, because 10's a positive number. Can you take the log of 10 minus 9? Well, 10 minus 9 is 1. Sure, that's a positive number, so the 10's a keeper. How about the -1? Can you take the log of -1? Of course you can. You've already said that the domain is greater than 0, so you know that that one's being chucked out. It's that type of work that we're dealing with. They do make things somewhat complicated. If we look at I think it's our 6th example, they want to make sure that you're okay with messing around with some complex stuff, because that's what we have in calculus. So we don't always live in happy math land where things work out evenly. Examples of that you saw here in number 4 and here in 6. Now, they're going to ask for two things in a problem like this that I saw in the homework. So again, I'm not making this up. This was here. They asked for what a calculus class would ask for, and that's an exact answer. Then they asked for the decimal, and that's running it through your calculator. You run this through your calculator and give us a decimal. 9 times out of 10 in calculus, that's meaningless. It was not helpful. We need to actually see the breakdown of the number because it's involved in something larger. So we're not going to do anything different. We're going to say, I need to solve this log equation. I either can get it into a single log equals a number, which it looks like I can do here, or a single log equals a single log. Let's get it into a single log equals a number. So that's the ln of x times x plus 4, just like you did in intermediate algebra, is equal to 3. What's the base? So let me back up for a minute. As soon as you have a single log equals a number, you should be thinking translate to the exponential. So we have e to the 3rd is equal to x times x plus 4. Okay. So what do we have? Well, e to the 3rd is just some number. If you remember, e is like 2.7 or something like that. Whatever, it doesn't matter. Okay, but I guess it does matter. I think it's 2.1718. But we're going to raise that number to the 3rd power. Okay, so we're going to get a number that's smaller than 27 but bigger than 8. Closer to 27 because it's below 3 but not too far below 3. So it doesn't matter. My point is that it's a number. E cubed is equal to x squared plus 4x. Beginning algebra would say, hey, get 0 on one side whenever you have a quadratic, everything else on the other. Now, e to the 3rd is not a variable raised to the 3rd. That's what I'm trying to stress. It's a number. You don't need your calculator to tell you what it is because they want it exactly. But we needed to solve this. Well, the only way to solve this is we don't know factors of some irrational number that are going to add to 4 because they don't exist. Well, they do exist, but they're crazy. So we just use the quadratic formula. X is equal to -b plus or minus the square root of b squared minus 4 times a times c all over 2a. Right? Something that I know you have memorized. -4 plus or minus the square root of 16 minus 4e to the 3rd all over 2. Okay, now we're smart. We know math because we chose this math science route. So we're going to simplify this square root, and you're not going to be surprised, but I'll walk you through it. You're going to pull out the greatest common factor of 4 and be left with 4e cubed. There's no way they're leaving that perfect square underneath there. But I'm going to model it for you. This is who they know you are. Somebody that can just wade through what is beginning algebra and come up with the right answer. Somebody that's going to be careful and know, I got to cancel 2's out from everywhere. So that's a -2 plus or minus. Actually, let me not write it up that high. Get here with an eraser. Right? They think you can just go right to -2 plus or minus the square root of 4 minus e cubed. Those are the two answers, except one of them we can't take. You know that -2, you know that I made a mistake, and I didn't even mean to make it. I just realized it. My mistake is when I brought the e cubed over, it should have been negative. What we had underneath that radical was a negative number because e cubed is definitely bigger than 4. It's a plus underneath all of these. I just realized that. I'm like, oh, it has no solutions, but I don't think they would have done that to us. But if they did, right, if for some reason it was a negative, we would have, if that e was positive somehow, and making that thing, making that move over a making that move over a positive. So if this e was negative and I brought it over as a positive, we wouldn't have had any solutions. But 4 plus e to the cubed is definitely a positive number. But it's definitely -2 minus that is going to be a really big negative number. So that one's out. The only answer they're going to put in the back is -2 plus the square root of 4 plus e cubed. That thing's going to be bigger than 2. The 4 is already bigger than 2. Well, it's the same as 2. And so that would have offset to 0, but the e cube is going to make it even bigger. And so it's definitely going to be positive. So that's our only keeper. Certainly we know a negative number minus a positive is even more negative, and we can't keep that because it's not going to work with this first term that needs a number that's positive. And so that's what they're going to do, is they're going to take something that's relatively straightforward and say, hey, you're going to be okay. They're going to do, and let's see what this last one's like that I wrote down. This is log base 1/4 of x squared plus x. And this time they did a minus. I didn't see too many minuses in the homework. Guess that's okay. What would we do? We'd write it as a single log. You know from your properties of logs that that's a division. You have a single log equals a number, so you know that 1/4 to the exponent is equal to what the log was operating on. Great. You know that 1/4 to the -1 is 4 because you went through pre-algebra. You know that to solve a rational equation, you're going to multiply both sides by the denominator, and you're going to get 4 times x squared minus x is equal to x squared plus x from beginning algebra, usually chapter 6, right after a factoring chapter. You know that you have 4x squared minus 4x. Through pre-algebra, you distribute that through. Okay, now we're going to bring over our x squared. You know you're going to have 3x squareds. We're going to bring over an x. You're going to have a minus 5x is equal to 0. You're going to factor out the x and get 3x minus 5 is equal to 0. You're going to say, oh, that means x is equal to 0, or x is equal to 5/3. Now, which ones can we keep? Don't know. Obviously, we can't keep the 0. If we go back to the original equation, which is right up here, 0 is going to be a problem. 0 will not work for these because we cannot take log of 0, and that's what that's going to be. So the 0 is out. How about the 5/3? Will that be a keeper? 5/3 squared plus 5/3, that's positive. 5/3 squared minus 5/3, let's check that out. So 5/3 squared minus 5/3. 5/3 squared is 25/9 minus 15/9. Absolutely, that's positive. It's just 10/9, so that's a keeper. It's definitely going to be positive over here because you take two positive things and add them, you're positive. So we're good. 5/3 is a keeper. It works in the domain. It solves the equation. Sometimes you keep both answers, though, so don't always think that you're chucking out one because there's plenty of times that you keep both. Seems though there's a lot of times where just one survived. So this is really good. They're trying to teach us to remind us how to solve rational equations. Beginning algebra, intermediate algebra, reinforced concept, negative exponents, pre-algebra concept, the quadratic formula, simplifying radicals, right? So that's from previous stuff. They want us to remember, that there's an unwritten base of 10 here, how to rationalize a denominator, all the good stuff, how to solve an absolute value equation. So many good things reviewed in the context of logs. Why? Because we need you to be reminded of all those skills, not just what logs are. All right, enjoy.